All right. Welcome to class today. Today we're going to do a bunch of stuff with the data that we've collected so far, right? So basically two main things. The first thing we're going to do is assess the accuracy of the drone-derived, oh, it's touchscreen now. Oh, cool. Wow, it wasn't before. So the drone-derived digital elevation model that we made last week. Wow. Or sorry, 2 weeks ago. So yeah, what you're looking at here is I took the data and I put it into ArcGIS. It'll do that. In fact, let me just show you the data structure that it creates. So after the project runs, you'll have these these three folders, 1, 2, 3. The other folders are I actually created the data folder just by accident, and now it won't let me delete it until I close ArcMap down. So that's why it's there. I was just making another folder for something else, and I made it in the wrong directory. But temp folder, you can go ahead and delete if you want to, like if you were running this. Basically, during the project, while it's actually running through, it creates a bunch of temporary files, and when it finishes a complete product, it moves that complete product back into this folder. Okay, so in your initial folder, you have the report that you see at the beginning. So that's the one that we've already looked at for Bayou Pierre. I guess you double click. Oh, there we go. Let's open it up in Google Chrome. So we did look through this already, and it gives you information about the number of key points that it found. In other words, in each image, how many interesting features did it find that it thought that it could match up with other interesting features in other images. So that's a little less critical than some of these other ones. Basically, see that it actually ended up not being able to match every single picture. Okay, there are some ways that we can try to get it to match more, either post data collection or before data collection. Before data collection, one thing that we could do in this area is fly higher. The higher we fly, the less differences there'll be per image. We talked about this before. We fly higher, get less differences in each image because the images will look a little different. I mean, they'll look a little less different because they'll be a higher up perspective and they won't change as much. And then, this wouldn't really be something you could do for this area, but in an area that wasn't basically, if you flew in an area that had more detail and less nature, I guess you could say, particularly the forested areas, those are the areas where it didn't stitch. In fact, we can look back here and see, there we go. These are the areas that didn't stitch up by the trees. So that's not unexpected. And then even in the treed areas, you can see that the expected error is pretty high. That's what these little ellipses mean. Okay, so not great. And you can see the result of that in this image right here. Right, this is the digital elevation model that created, and the accuracy in this area is just really, really poor. But we're not really interested in that. We're interested in how the stream channel is changing. Okay, so we're mostly interested in that area. So that's what we're going to assess the accuracy of that digital elevation model to see how well it did, because we're interested in using this technology to study the stream morphology over time. So we're interested in knowing basically what level of precision that we can report for this area. Okay. All right. So let's see if there's any. Yeah. So there's very little difference between initial basically the internals of the camera were very well known, and it didn't have to like apply a lot of distortion in order to make the images fit together. It didn't have to like kind of force them into place and wiggle them around a lot. If this number is below 5%, you're good. So this is like really good for the images that it used. Oh, one more thing you can do to see if you can get more image calibrated is that you can manually go and find interesting points by yourself. It doesn't always work, but there are cases where it does. I should show you an example some other time with the coral reef studies that we've done. And sometimes after it's finished, the coral reef will won't stitch. Like it'll be stitched together here, and then there'll be a whole nother piece right there. And in reality, they should actually be connected. And if you go through and identify, oh, those are two places that are definitely the same thing, and then re-optimize, it'll work better. So re-optimize. Oh, yeah, we'll do that in a second. All right. So this indication of RMS error or RMSE, sometimes we call it RMSE. Here they're calling it RMS error. Look at what that's in meters, right? So that's 2.3 centimeters. Am I correct there? The hundredths. So hundredths of. So right now we're saying that the RMSE is 2.3 centimeters. Now what that RMSE is telling you is not how accurate it is. It's telling you how well it fit the model that it created, this digital elevation model. Okay, let's make sure that we all understand what this is first of all. So this is a raster data set, an image, and every single pixel represents what? Elevation, yes, that's what that is. The height above a datum. Okay, in this case we chose the datum, and I forgot exactly what it was, but anyway. So the RMSE is 0.023 meters, and that's how well this matches those ground control points that we went out and took, similar to what we did last week. Okay, but 4 weeks ago when Dan and Frank and I were out there, we took some GPS measurements, and the reported accuracy of those GPS measurements by the company that creates the GPS is somewhere in that same range. So that's also really good. So this is really good in terms of that's probably as close as we're going to get, because the GPS itself has a reported accuracy in that range of 1 to 2 centimeters. So we're just barely outside that range. So we did a good job at identifying those, and the Pix4D was able to match it. If we had, let's say, like made an error of like 2 feet or something in one of our ground control points, then this number, we'd expect that number to be higher, because it would have a harder time adjusting all the internal camera parameters to fit through all those points. Because we've stuck what was it, 12 GCP points out in space, and said, do your best to fit through all of these, to fit this digital elevation model through all of those points. And what it's saying is, this is how good I did. That each of your ground control points, if I take the error of each of your ground control points as I fit them through these 12 points, the error is only 2.3 centimeters overall. Okay. So the true location of those, not the true location, but the GPS measured location and the measurement in this data set are only off by 0.23 meters. Okay. So we can have a fair bit of confidence that this is. We can have a fair bit of confidence that this is a well measured. it's in its location. It's in its proper. It's well fit into its proper location. Now, what's probably more interesting though, but it's necessary to have done this. It's more interesting to know if any arbitrary location in this data set is also of a similar accuracy. Okay, we might be concerned with areas that are below the water, which we're concerned a little bit about. We want to see if we can profile the water underneath the water with those. We might also be concerned with the how well we could tell the growing and the shrinking of these dune features. Okay, so if we can come up with another RMSE measurement that tells us how accurate we are in those areas, then we know to what degree we can report a change in elevation. So if we say, well, if we come back a year later and do the same thing with the drone, and there's been, let's say, a 7 centimeter change in elevation, is that significant? Is that something that we can report? Well, this is what's going to give us an idea if that's something that we can report. Okay, this next step that we're going to do in assessing the accuracy. My guess is 7 centimeters is probably pretty close. We might not be able to do that. So we'll look at that. Okay. All right. So that's what we're going to do next. All right. So anyway, yeah, that's the quality report. That's what you see in the initial folder, and then inside the densification folder is the point cloud. The point cloud is usually produced, unless you tell it otherwise. It's produced in this format called a LAS. It actually stands for laser scan. And initially, point clouds were mostly the result of a LiDAR data set. Okay, and so it divides it up. The LAS files, it doesn't let them get above a certain threshold. I forgot what it is. And so you may see 1, 2, 3, 4, 5. You may see 10. I've got about 15 in the project that I'm processing for the coral reefs that we just did last month now, and it's already above 70 gigabytes of data. How much is this? So this is only 3.2 gigabytes. So our project though had 7,500 images, and this project still had, I think, almost 2,000 images. Is that right? It was on the report. It still had a lot of images because it was a multi-image data set. Okay, they also give you this 3D mesh file. The 3D mesh file is a file that some software programs can read. It's kind of nice not having to walk over there, but I got to get used to the fat fingers. But the files that it creates are these MTL, FBX. Basically, it's some programs can read this and create a three-dimensional data set. ArcGIS doesn't read this, but there's actually a website called anyway, there are a few websites where you can upload models. Why can't I think of it right now? Yeah, so it's not this. I don't think it's this. Is it Shapeways? Maybe that's the one I used for 3D printing online. Yeah, that's the one I used for 3D printing online. Sketchfab. That's it. So you can actually, I think you can create things here, but you can also use Sketchfab to upload these very files. Now Sketchfab has a limit on the size that you can upload. I used my Facebook, but I never remember my Facebook password. changed about a year ago. Oh, good. All right. Memory's better than I thought. So, so I've uploaded some of my other ones. I haven't uploaded one for a long time, but you can see some of the ones I've uploaded here. Yeah, so here's Red Bluff. Okay, I did this with my daughter, and when it was done processing, I uploaded to Sketchfab, and that allows you to like, share it online. So they do charge. There's a free version, and then there's like a second tier version, and there's like a super duper version for like really big files. The second tier version is free for EDU email addresses. So that's what I have, is that second tier version. I still think it's under 200 megabytes for a model, which is pretty big, I think. Let's see how big the model that we just created here is. So it's this zipped file that you'd set up. So yeah, ours is only 43 megabytes, so we could upload that to that website. And you can control how detailed that model is. Obviously, it's not as detailed as the other products that we're going to deal with today, right? It's not as detailed as the, well, when I say other products, we'll go on to the next topic here. The other products, the ones that we're going to deal with today, are in the last folder. Okay, the DSM, the digital surface model, and the mosaic. Okay, let's see how big these are. So that's 1.9 gigabytes. So it's like way bigger than that model that it created. So it's a simplified version of it, but it does a pretty good job at condensing it down. But obviously you lose, some of the precision. If we zoomed into that Sketchfab model, which is still up, you could see that there's some generalization going on there. Okay. All right. So then here's the mosaic, and that is 2.5 gigabytes. And that's what I'm showing here in ArcGIS. So they're just, by default, most of these software programs, including Pix4D that generate these things, will export it as a TIFF. Okay, a TIFF is an image format. Some of them will let you specify other formats, but TIFF is the most common format that it will allow you to export the data into. Okay, so here's our TIFF of the imagery, and then here is the TIFF of the digital surface model. Now, one of the big problems with this is that in all the areas where it's most inaccurate, it's really, really tall. And we're not really concerned with those areas. So one thing that we could do is to change the symbology over here to make it more so that it would reflect just those areas that are low, right? I'm going to go over here because it's a little more comfortable. So we could go over into symbology. And I'm going to make it so it's not so many crazy colors either. Let's just do maybe 3 colors. And it does take a little while to draw. In fact, it takes a whole long time to draw. So maybe I'll only do this once. But so you can see all these really high values. This is a histogram, okay? And I'm going to go ahead and move this first and then talk about it because it takes so long to draw. And I'm not sure why it's taking so long to draw. It doesn't take very long to draw in Pix4D, but it does take a fair bit of time to draw here. So this is a histogram of the data. So in other words, these tell you the amount of pixels that have a certain value. And so our low value there is in the 50s, and our high value up there was really high. I forgot what that number was. Anybody remember? I don't remember, but really, really tall. The tops of the trees and even beyond, because it kind of extrapolated out in those areas. So what you can do, what you're doing here, is you're saying, hey, I only want to look at this area right here between 50 and 52 meters. This is in meters. So this is like a 2-meter zone. And so it's going to take all the color and it's going to stretch it in just those areas and display that a little bit better. Okay, but it may take a little while. While it's doing that, we can go ahead and set up to measure RMSE because it's not that hard. It's a simple formula, and the easiest way to remember it is by taking the numbers. Taking the letters and remembering what each of them means. So it's root, mean, squared, error. Root, mean, squared, error. And you kind of have to apply it backwards. So we're going to first find the error. Then we're going to find the average error. Then we're going to, root, mean, square. Then we're going to square the error. So first we're going to find the error. Then we're going to square the error because we're going backwards from RMSE. So first we're going to find the error. Then we're going to square the error. Then we're going to take the mean of all the squared errors. And then we're going to take the square root. So that's how you calculate root, mean, squared error. Okay. All right. So the first step that we're going to do is to go back and get all of those points that that represented the elevations. Okay. So I had those as a shapefile last week already. So those are under C UAV course by Pierre, and then just UAV course by Pierre, and then the GeoRef. That's right. So I got my Bayou Pierre checkpoints. I'm going to turn this one back on just because I need something to kind of provide some reference here for where we were. Okay. So these are all of our points. And I think the first thing that would be helpful is to kind of categorize these points so that we can calculate the RMSE in different areas. Okay, the root, mean, squared error. So we can provide a statistic that says, okay, well, this is how accurate it is overall. This is how accurate it is on the dune. This is how accurate it is in high slope areas. We've got a couple of those right here. And then this is how accurate it is in the channel. I thought he had more channel points up here, but I guess he only has those channel points down there. All right. Okay, so if I look at the attribute table here, I can get an idea of all of these points. Now, remember last week I said that we should not include any of the target points as the we shouldn't include any of the target points as checkpoints. So the first thing that we could do is kind of like, well, when we create categories, we'll create those as their own category so that we don't include them in the overall value. So I'm going to add a field here. I'm going to add several fields. So the first field I'm going to add is just going to be called category. And I'm going to make the data type for category text because it's just going to be whether or not it's a ground control point or it's going to be the kind of land cover categories that I'm interested in testing. So basically, I think I'm going to have three. A forested, a sandbar, and channel. Okay, so we'll have those three. And these three are kind of different because these are forested, and so maybe I'll have another category for just those. This one right here is a ground control point, so it's not going to be included anyway. These other three are are up against, are on the embankment, which would be interesting to know how accurate it was there. But I'm also concerned that there was so much forest right there. I should have had Frank maybe get some of these guys, but we can check that out later. All right. Okay, so text, and then that's going to be category. And then yeah, length 255 should be sufficient. Click here to add another new field, and then we're just going to have error as a field. This one's going to be a double precision. Okay, what I want to be able to store a number that's very precise. I guess technically it probably doesn't need to be a double precision number because we're really only, we can't hope that any of this is any better than the RMSE for the overall data set. So that's 2.3 meters. So if we wanted to save some space, I guess we could say this is just going to be a float. Okay, single precision. We're still going to get decimal places, but I don't know, like 5 or 6 decimal places instead of 15 or 20 decimal places. All right, so that's fine. Okay, so now I'm going to hit save. What that does is it saves those 2 extra fields. There are actually a few ways to add fields in ArcGIS. Okay. All right, and now I can go and close this pane. Yeah, I thought I saved. I did save, right? Let's see what happens if I say okay. See if those fields are there. Yep. Okay. So now what I can do is just manually select. Maybe if I had more points, this would be a little bit more difficult. Well, actually, the first thing I'm going to do is to manually select the points that are ground control points. So it's those 12 points. So the first 12 points that we collected, and I'm going to calculate a value into that, and that value is just going to be something like GCP for ground control point, because I do not want to include these values in my overall calculation of accuracy. And you see how it's hard to see, but this one got highlighted. Oops. That one got highlighted, the one I told you was a ground control point. So those got highlighted, and now I can just say equals quote GCP quote. So now it's going to store the value GCP in those data in those data points. Okay. All right. So for the next, close that up for a second. So for the next one, I'm going to use the select with a lasso or a circle, polygon. Any of these will probably work. And I'm going to select all of the ones that are in forested areas. So I'm going to select out this kind of marginal right there. I'm going to select it. I should probably make a distinction because like this one's just way too far. I don't know why Frank went way in there, because the drone didn't even really fly out there. That's the very edge of the data set, but yeah. I think, let's see if this one drew yet. Nope, still not drawing. Yeah. Okay. Yeah, I think what I'm going to do here is actually, I'm going to throw those other 2 out. Like I'm not even going to use them because they're out into the woods. So we'll call these guys. Open up the attribute table. Oh wait, are there any more forested ones? I should look because oops. I should make these a different color Huh. Okay. Yeah. So there's a couple over here. Are these still selected? Okay. You know, this has taken a long time, so actually maybe what I'll do, it's just taking a long time to refresh. So maybe what I'll do here is clear the selection, and then we'll do the finding the values first. Okay, ArcGIS is good at this. It'll run as a tool, and then we'll calculate the error, and doing that will kind of help us to highlight the ones that are truly horrible that were at the edges. Okay, so that way we don't have to do so much hunting and pecking around. Right? So under geoprocessing, there's a tool called extract values to points. Now, if we look at the help here, well, actually, I think I could have just hit that question mark, but what it does is it extracts the cell values of a raster based on a set of point features. So it takes a bunch of point features and it looks at the raster cell closest to the point feature, and it takes that value. Okay. So that's what we want. So we're going to take our by UPR checkpoints, and we're going to take the input raster is going to be which one of these two? Do we want the brightness values, or do we want the elevation values if we're trying to check elevation error? Yep, so we want the elevation values, and it's going to create a new data set for us, which we could store in the same place. I'll store it in C, UAV course, by UPR, GeoRef. I'll just call it checkpoints with elev, for with elevation. Okay. All right. Now, these options that exist here, this first one says interpolate values at the point locations. What that does is it uses IDW and says, okay, it's not in the very center of this cell. These are the three closest cells, and so I'm going to take the average of those three closest cells weighted by which one is actually the closest. So I'm sure there are arguments for using one or the other. What size are our cells, by the way? We could find that out, actually, before we even run it. It was in that report, but it's also right here. Okay. Our cell size is 0.19, so 1.9 centimeters. Okay. So it probably doesn't actually make a whole lot of difference what you select. That's so tiny that it's only going to be considering the cell that it's in and over 2 centimeters and around 2 centimeters. It's just a really, really small area. So for our particular application, it'll run slightly faster if we don't check that button. However, if you were dealing with less precise data, you might want to check that because you'd be getting the average of the nearby values and you wouldn't know exactly where you are. During like wind and stuff. Yeah, I mean that's definitely one of the reasons. Yeah, I mean it has a difficult time stitching trees together because of that reason. Yes. Yep. All right. So I'm going to say okay, and I'm going to leave that blank and just hit run. And so now it's going through and it's finding the value of the by UPR data set at all of these locations. That's what the new blue points are. So if I open up that data set, then I can see that now I have a new field called raster value. Okay. I also have the field that Frank collected, called GPS height. See 50.515, 50.4949. So that, whatever that one was, is pretty close. It's not surprising. Why is that one not surprising? That's the first one that we collected. It is a ground control point. And so we knew that all the ground control points were only 2.5 centimeters off at the, well, it's the root mean squared error. So some of them are a little bit more, some of them are a little less, but yeah, that one's down here, right there. So that was one of the ground control points we collected. All right. So now we need to follow our formula to calculate root mean squared error. So the first part of the formula, if we work backward, is to calculate the error. Now what's the error? How would we calculate error? We've got, this is the modeled value, and this is, oops. Oh, there it is. Okay. So this column, yeah, this column right here is the measured value. In other words, what we went out there and measured with a high precision GPS. And this column here is the modeled value, what we're getting from the drone. The drone's reporting, the drone DSM is reporting that value. Okay, so we've got those two values. So with those two values, if we wanted to calculate error, we just simply subtract. Okay, subtraction is the way to find difference, right? We learned that back, I forgot, probably in kindergarten or second grade, first grade, somewhere in there. So let's add another new field, and we'll call this error. Oh no, we already did it. Sorry. Okay, I'm just gonna close this up. Sorry, we already did that. Okay, so to calculate error, we want a positive value if we overpredicted, and a negative value if we underpredicted. So how would we do that? Well, if we want a positive value when we overpredicted, then we would have to take this value, the modeled value, and subtract it from the measured value. Because if it's higher, we'll get a positive value, and if it's lower, we'll get a negative value. It actually really doesn't matter in the RMSE calculation which order you do it in. You'll get the same number for RMSE, right? Because the next step after error is, if going backwards, is that we square it. And what's the square? What's negative 2 times negative 2? It's 4, not positive. I mean, not negative 4, it's 4. Okay. Oops, I didn't mean to do that. I'm getting all these crazy. Okay. Okay. I'm trying to make this one bigger. There we go. Not that big. Okay, so that's error. And I said we needed to take the raster value and subtract the raster value from the GPS height value, or the GNSS. So what's the difference between GPS and GNSS? Right. So, 15, 20 years ago when I started teaching, the U.S. government satellites were the only satellites out there, and the U.S. government called them the Global Positioning System, GPS. Now there are multiple GNSS, Global Navigation Satellite Systems out there. So there's lots of them, and so technically most what we call GPS systems out there, particularly the high-grade GPS systems, acquire satellite locks from all of the systems out there, or at least multiple systems out there. So so GNSS is technically the correct term to use, but we often still say GPS, right? Oh, I need to clear. There we go, and run it. All right, so now we've got this new column that has the error, and whether or not we overpredicted or underpredicted is shown by the sign. Okay, so of the first 12, let's make this a little bit bigger. Of the first 12, how many are over even a centimeter in terms of their absolute error? Well, oh wait, this is still in meters. Yeah, so actually lots of them are over a centimeter. Some of them, one of them is almost a meter. Look at that one right there, 8. Okay. No, not a meter, almost a decimeter. Yeah, 15. So these are higher. These are higher, but some of these are much lower. Okay. All right. I wonder what, like this is the very highest one. Let's see where it is. So this is the ground control point with the highest error. Oh, it's that one right there. And we were kind of worried that one got moved. I don't know. That's interesting. This one is the second highest error. That's that one right there. So it would be interesting to note if the errors were had a pattern to them. If the errors have a pattern to them, there's probably something that we could do differently in the processing. So sometimes it's interesting to actually look at that error and see what it looks like. So we could go to, the symbology and choose graduated colors. I'm going to make these format all symbols. I'm going to make them bigger. And then re-choose this. I'll choose like something to red. Because the higher it is, the more, well, okay. Actually, I should probably choose some diverging one. Well, let's wait to symbolize them till we do the next step. So here I'm going to clear this. And so that's the error. So this is showing the error, but the errors are negative and positive. Okay. So some of them are really, really big, 24 meters. I'll bet you that's one of the ones that's over here. Oh, that's that one. Yeah, also in the middle of the forest. Okay, so likely it's got the top of those treed areas. Okay. But the first thing I'm going to do here is clear this and calculate the squared error. That's easy, right? I should have actually made a field for that. So I'll call this SQ error, and I'll also make that a float. Yeah. And then that's it. That's all you need. Save. So what we need to do is to calculate the squared error into that field. There's a few different ways we can do that, but probably the simplest way is to just take the error times the error, which is the same thing as the error squared. Oops. All right, now calculating the overall root mean squared error is pretty easy at this point. We could just go to statistics, I think. Statistics or summarize, I always forget which one. Okay, so here's the mean squared error, 16.305983. So that's the mean of that whole column. So that's the mean squared error. So to get the root mean squared error, we take the square root and we get a value around 4. So of all of the points, the root mean squared error, which is a statistic of the average amount of error, is 4 meters. So that's pretty bad, right? So, my guess is that it's because we have some really, really bad squared errors, which we do, right? Some of them, the absolute error was 24 or 18, and so the squared error becomes 353. That's pretty high, right? Where's that other one? All right, so let's take out the points that we don't that we don't think we should even include first. So I'm going to sort these by the squared error, descending. All right, so that's this one. That's obviously one we should remove. That one we should definitely remove. Let's see where this one is. Ooh, that one's like right on the edge of the forest. It's kind of interesting. But yeah, I don't think that's an accurate measure. That one's in the forest. Oops. Am I holding down the right key? Shift, shift, shift. Let's see where this one is. Even that one is pretty much in the forest. Let's see where this one is. Okay, that one's not on the forest. So let's just get rid of all of these guys, because those guys are definitely in the forest. Now I wonder if there's any other forested ones that we didn't select. That's one, right? I'm going to close this guy down. I'm going to make this bigger. Anybody see any other forested ones that might be good candidates for removal? So that's one thing about drone data, is we're not going to get a good representation of the ground in forested canopy. Okay, so yeah, I think those will be fine. Those are the worst offenders in terms of root mean squared error. So I'm going to change all their categories to, I'm going to change all these categories to ignore. I got to put it in quotes. All right. So now I could I'm just going to do this manually. I could actually, well, no, I'm not going to do it manually. What I'm going to do is sort, we'll do it manually. Sort by category, and then highlight all of the ones that don't have a category yet. So this will give us our true overall root mean squared error for only those points that we actually meant to calculate the accuracy of. Now, interestingly, these 2 points are in the woods, but their root mean squared errors are pretty good. I don't know exactly what they are, but they're pretty good. I mean, their errors are pretty good. We could probably remove them though. So let's calculate the squared error here. So now we can right click again and say statistics, and it will only work on those. I thought it would only work on those selected. Let's see if there's a, yeah, we'll just do it this way. This produces an actual new data set. So I'm going to take the squared error and find the mean of that data set. And then I have a case field here. So my case field is going to be the category. So for right now, I only have 3 categories: blank, ignore, and GPS, or GCP. So I could I can further separate my categories out later. So let's look. Is this running? There it is. I guess it just puts it there. Okay, so here is our mean squared error. Now, that looks like it's too small, right? What happens when we square root this? What's going to happen? It's actually going to get bigger. It's a weird thing about square rooting things. If it's a number over 1, it gets smaller, and if it's a number above 1, it gets bigger. So we need to take the square root of this number. I'm just going to do that in a calculator. Square root. So the square root is 10 centimeters. So the root mean squared error is 10.27. Okay. So when I said 7 centimeters might be a little bit too optimistic, we got pretty close, right? So what that's telling us is that if our errors are normally distributed, in other words, if in some areas they're low and high, but they're spread throughout the area, and the errors themselves look to be kind of well, on a bell-shaped curve. There's some high error, there's some low error. They're all going to be apart from each other. If they are in that normal distribution, we can expect that roughly 70% of the time will be within 10 centimeters. Okay, 1 standard deviation out. So RMSE, if you've taken a statistics course and you've calculated standard deviation before, it's almost the exact same formula. Standard deviation is calculated by taking all of the values and taking their differences from what? The mean, exactly. So we're treating the modeled surface as the mean in this case. So the modeled surface is the mean, and when we calculate root mean squared error, we've just calculated standard deviation, except for instead of using the mean, we use the modeled surface. With standard deviation, you're using a mean value, and you're calculating the average difference from a mean. We're calculating the average distance, not quite the average distance. It's the root mean squared error. It's the root of the average squared distance from in this case from the modeled surface. So that's our overall value, 10 centimeters. If we wanted to find out where we could expect, let's say, 98% of the error to be in, that's like 2 standard deviations out. Is it 98 or 97 point something? Now, those of you who've taken a statistics class probably recognize that number, but 2 standard deviations from the mean. About 95 are within 2 standard deviations. Oh, and about 95% are within, and about 97 lie within 3 standard deviations. So we could just, multiply this. So a little over 20 centimeters, 95% of the time, the checked point is going to be within 20 centimeters. So we could expect, as long as our errors are normally distributed, any random point in this whole area, we could expect to be within 20 centimeters 95% of the time. Okay, so that's the kind of thing that would report to somebody, and the kind of thing that we would use in order to assess any changes that we saw in this landscape over time. Okay, did it make a change that was within 2 standard deviations? If it did, we could say there's a really good chance that it was a real change, that it wasn't just some measurement error that we made either in time A or time B. Okay. All right. So that's why we calculate that number and its use. Okay, so let's just look real quick at that number. This never drew. It took like 20 minutes to draw last time, so it doesn't really matter. We don't need to see the. We can look at it in Pix4D. Okay. And for some reason, it draws just fine on my desktop. So I don't know why this. It's just this particular computer that's drawing. Well, maybe it's other computers because your computers are the same as this one. Okay, let's do one more where we're just concerned with the. Well, now it's going to be hard to tell what just the ones on the dune look like. But we could go something like this. We can at least be sure that let's say I don't know for sure whether those are on the dune, so I'm not going to count those. Pretty sure those are on the dune. That's a ground control point, so I'm going to eliminate it anyway. So the ones that aren't highlighted now are the ground control points, or they're in the forest. Okay. So I selected. Did I reselect? Yeah. Pretty sure all these guys are on the dunes. Even this guy's on the dune. But some of these guys are forested. It's like an academic exercise. All right, so I'm going to open these up. Sorry, not those. The checkpoints with elevation. And then I'm going to sort these by category. And then I've got to remove the ones. I only want to see the selection. So I can say, okay, I only want to see the selection. How do you do that now? Yeah, right there. Okay. So I'm going to take out these data sets that are just GCP. It's like double selecting them. I don't know what double select. Our map doesn't have a double select thing because now they're yellow and blue. So basically, what I'm trying to do is get these points right here that I think are. Well, clear the selection. Okay. Well, let's just select a few of them. Select. That's not really enough. Okay, these are all. Those are all sandbar points. So let's look and see if we can really quickly get a. I want to summarize on squared error and see if we can get an estimate of what it would be just for that area. So now we're going to go to squared error. We're going to get the mean. And I'm just going to Just going to say just the selected ones. See if this is lower. We'd expect it to be lower. 0.014. That's actually not lower, is it? Oh no, square root. Yep. So that's actually not any lower for just those points. Okay. It'd be interesting to select all of just the sandbar points, because some of these aren't necessarily sandbar. Sorry it's taking so long to draw. If it wasn't taking so long to draw, we could get a better idea of categorizing each of these out. But the point here is that we calculated the overall root mean squared error, at least throwing out the points that are like in the tree line, and I've kind of talked about why it would be important to do that. So anyway, anybody have any questions about that? All right, so yeah.
We're really only calculating the error on height, right?
As opposed to, oh, like the color? Oh, how far off it might be? Yeah, so we're taking the perspective from a person that was interested in, using the data, how far off it would be. So, yeah, I mean, it might be that the reason that we're off is because we're also off in the XY dimension, right? But we want to know for a given location what the error is. Yeah, it's usually the way it's used. But yeah, there are people that have researchers that have experimented with being able to have that accuracy, and you would need something marked. So we would have to have marked locations that weren't checked, I mean, that were used in the model, which we could leave some of them out and use those. So yeah, there. But yeah, if we had what he's saying is if we had several marked locations, we could find out in 3D space how far off the marked location was from the measured location when we measured the mark. So we could find out its XYZ location and find out its new XYZ location, and then take the difference. Okay, which is really just it's a math problem too. It's a little bit different math problem, but we're taking 2 points in space and finding out how far away they are in X, Y, and Z space. But yeah, this is the way it's reported in lots and lots of research articles, kind of like a user's accuracy assessment. If I was going to use this to measure, to use this map to actually measure stream channel changes, well, what would I expect the accuracy to be? It's a good question, though. All right, any other questions? Okay, what we're going to do is take a 10-minute break, come back 5 minutes before the hour, and I'll just leave this thing going. And I'm going to move the data over that we collected last week and that I've already processed, and we'll talk about how I processed it and what we can do with it. It's basically radiometric correction. I uploaded right before class a short little lecture that I'm going to go through, 10 slides or something, on radiometric correction. So I'll do that. I think I'm going to stop the recording and then restart it.